When you write this simple addition code on the screen, what do you think will happen? Many people subconsciously assume that the system will do three things in order: automatically create variables, store the corresponding values into designated memory spaces, and finally complete a mathematical addition operation. But the reality is, from the hardware's low-level perspective, the three layers of high-level language logic we understand do not happen directly at the CPU level. The CPU does not know what a programming variable is, does not recognize the int data type, cannot understand the assignment equals sign in the code, and cannot directly parse a mathematical addition expression like a plus b. Strictly speaking, the CPU never directly runs the high-level language code we write. It does only one thing its entire life: unceasingly fetches, decodes, and executes binary machine instructions one by one, with no extra logic understanding, only fixed hardware actions. The C++, Python, Java we write daily are all high-level programming languages, artificially designed to fit human thought logic, specifically written for programmers to read. Computer hardware, the CPU, cannot directly recognize or natively understand these codes. From the moment you write the last line of code and press run, to when the hardware actually starts scheduling and running, a complete closed-loop translation and optimization pipeline must be completed. Take compiled languages like C or C++ as an example. The full process is as follows. Step 1. Lexical and syntactic pre-check. The compiler scans all source code line by line, splits keywords, identifiers, operators, checks syntax format, variable definition specifications, symbol pairing, keyword usage rules, and identifies explicit errors and hidden syntax vulnerabilities. If the check fails, compilation terminates immediately. If it passes, proceed to the next step. Step 2. Global semantic analysis. Using the full code context, clarify variable scopes, function call chains, data dependencies, decompose multi-level nested logic, mark key nodes such as operations, memory, reads, writes, logical jumps, and automatically eliminate redundant dead code. Step 3. Multi-level code optimization, divided into front-end language optimization, mid-level IR optimization, and back-end hardware adaptation optimization. Combined with CPU architecture, multi-core capabilities, memory bandwidth, and other hardware configurations, merge duplicate operations, streamline redundant instructions, reduce resource overhead, and improve runtime efficiency in advance from the software side. Step 4. Generate low-level instructions. After multi-layer optimization, the intermediate code is finally compiled and linked into pure binary machine code. Assembly is only a human-readable mnemonic, not a necessary step for hardware. What is finally sent into the CPU instruction queue is only machine instructions composed of O south and 1 south, queued for hardware scheduling and execution. Our 3 simple lines of example addition code, after the entire compilation and optimization pipeline, are eventually broken down into just a few extremely simple hardware instructions. No variables, no data types, no abstract mathematical expressions. Only 3 core things throughout: CPU high-speed registers, raw binary numbers, basic hardware arithmetic, and read-write operations. So the core truth is very straightforward. The code you write is just a textual abstract description of the business logic. What truly runs inside the computer, consumes computing power, occupies memory and hardware resources, is the completely different binary instruction stream after compiler transformation. Then how does the CPU work at the bottom level? We use a standard, easy-to-understand basic model to see the essence of its operation. The complete CPU pipeline is divided into 5 steps: fetch, decode, execute, memory access, write back. Step 1. Fetch. The CPU core actively fetches one waiting binary machine instruction from a designated memory address and sends it into the core's execution unit. The entire process takes only microseconds. Step 2. Decode. The CPU's built-in dedicated hardware decoding circuit quickly recognizes what this string of 0 and 1 requests. Is it moving data, arithmetic operation, address jump, cache read or write? There's no thinking or logic judgment throughout, only matching fixed hardware actions. Step 3. Execute. Invoke the ALU, arithmetic logic unit, registers, memory channels to complete physical operations such as data movement, numerical calculation, logical jumps. Step 4. Memory access. Read-write memory data as needed to complete data interaction. Step 5. Write back. Write the operation result back to registers or memory to complete a single instruction loop. The CPU inherently does not have logic understanding capabilities. It cannot read programs, recognize functions, nor understand our business requirements. It is always trapped in an infinite loop, cycling billions of times per second. Simply summarized as: fetch one instruction, decode, execute, then fetch the next. Repeat, cycle, and nothing more. At this point, a counterintuitive piece of knowledge emerges. In a programmer's understanding, code always executes line by line from top to bottom, sequentially. What is written earlier runs first, what is written later runs later. But at the real CPU hardware level, this order is not absolutely enforced. To squeeze out all computing power, fill pipeline cycles, eliminate hardware idle time, reduce program latency and power consumption. Modern CPUs incorporate mature hardware scheduling mechanisms, the core of which is CPU out-of-order execution. Here, it is essential to distinguish two easily confused concepts. The compiler performs software instruction reordering during compilation. The CPU performs hardware out-of-order execution during runtime. The two act independently and jointly affect performance. The CPU's out-of-order execution has strict safety constraints and will never break the final result of the program. As long as two pieces of code have no data dependency, do not share memory resources, do not occupy the same register, and do not affect each other, the CPU determines that execution is safe. It then autonomously reorders the original instruction sequence, adjusts execution timing. It can also mobilize multi-core resources to execute multiple instructions in parallel. For example, two independent assignment codes that have no data relationship with each other. The CPU can completely ignore the original code order, executing the later line first and then the earlier line, or execute both instructions in parallel simultaneously. Throughout, there will be no errors, no logic confusion, only significantly reduced runtime and improved hardware utilization. A more advanced hardware mechanism than out-of-order execution is the well-known branch prediction. The frequently used if-condition judgments, if-else branches, ternary operations in development all trigger branch prediction. From the software logic perspective, conditional judgment must be executed serially. First, compute the condition, then select a corresponding branch based on the result. Neither step can be skipped. But the CPU does not rigidly wait for the condition computation to complete. To avoid pipeline stalls, it quickly predicts whether the current condition is likely true or likely false, based on historical execution patterns and branch trigger probabilities. After making the prediction, the CPU starts speculative execution, prefetch branch instructions, execute the logic of the predicted branch in advance, and temporarily cache the intermediate results. When the actual condition result is computed, it directly reuses the pre-computed data, saving waiting time. This is the core underlying guarantee for the smoothness and responsiveness of daily software. But branch prediction is not 100% accurate. Once the prediction is wrong and opposite to the actual result, the CPU triggers a rollback mechanism, discard the temporary data from speculative execution, invalidate the preloaded instructions, and serially execute the correct branch logic from scratch. At this moment, the pipeline is interrupted, computing power idles, resources are wasted, and the program experiences a brief stutter, frame rate fluctuation, or latency jitter. This is a core cause of many hidden performance issues. At this point, we can draw a key conclusion. The rule that code executes serially from top to bottom is not a hardware native rule. Rather, it is an abstract illusion jointly built by the operating system and compiler. This illusion is specially designed to fit programmers' thinking habits, shield the underlying differences of different CPU architectures, lower the barriers to development, debugging, and collaboration, allowing us to focus on business logic without worrying about low-level hardware details. The root causes of all performance issues, hidden bugs, and optimization difficulties encountered in development lie in the CPU's low-level design. Out-of-order execution, branch prediction, multi-level caches, pipeline architecture. These seemingly low-level hardware knowledge are the fundamental essence of performance optimization. Once you understand the CPU's entire operational logic, you have truly crossed the low-level threshold of development. No longer just stacking features, but able to read code efficiency, grasp performance logic, and write high-quality, stable, hardware-friendly code.